So now we have our next mystery, the mystery of why this simulation didn't load well. Just kidding, that's not the mystery we're looking at. We want to figure out how come these things, these objects, how come they reach the bottom of our ramp at different times. So what we want to analyze first, and we kind of want to keep the last thing in mind. So in the last part, we defined this rotational kinetic energy for that tic tac. We said, hey, this tic tac has this quantity, and that helps us explain what we're seeing in this actual situation. So we want to kind of keep that in mind when we're looking at the LOL diagram for these objects that are either sliding for the cube or rolling down the hill for every other one. So what I want to first do is do an LOL diagram for just the frictionless cube, and then we'll do one for another object and kind of compare them and see, hey, how did these things compare to each other? And how can we explain why these things, these objects, why they all rolled down the hill at different rates? So first, let's look at this cube. At the very top, this cube, I'm going to draw it badly, it wasn't moving. And we know that objects that aren't moving and are at some height above zero, those objects have gravitational potential energy. And sorry, let me define it as the cube and the Earth. So objects that are at some height and not moving, they have gravitational potential energy. And at the end, this thing, it was just kind of moving and it was at zero height. Let's just call that zero. Zero height, so it has just kinetic energy. All of this gravitational potential energy turned into kinetic energy. So that's all well and good. We've done that before. We're used to it. But let's then go on and let's analyze another object with the same method, the same LOL diagram. So let me make a quick copy of this. And we'll analyze this for, let's choose, I like the sphere, why not? Let's go with the sphere. So the solid sphere, sorry, not the lame hollow sphere. I don't care about the shell. I care about the solid one. Come on. So let's go with the solid sphere. And we saw, maybe we can look back at the simulation, you guys have the link. But we saw, okay, at the beginning, this solid sphere was just kind of sitting here. It wasn't rotating. So we know it still has gravitational potential energy. Let's pretend it has the same mass. I think in the simulation, all the m's are the same. So let's pretend it has the same mass as the cube, which means they have the same starting potential energy. But as we moved on, the rate of transferring our gravitational potential energy to kinetic energy, that was clearly different. They didn't reach the bottom at the same speed, which means it wasn't gaining that velocity as quickly. It wasn't moving as fast. So yes, it's still moving at the bottom, but we also saw that it was rolling. So let's, instead of just saying all of that energy went to translational kinetic energy, so the kinetic energy for something that is translating or just moving back and forth, let's say it has some of this translational kinetic energy, the kinetic energy that we're used to, and we saw that it was spinning. It had some of this rotational kinetic energy. So some of the gravitational potential energy went to making it move down the hill, but some of it made it go to rolling. And if we look at these and we compare them, this explains why it didn't get to the hill, as the bottom of the hill, as quickly. In the cube's case, the cube, all of that gravitational potential energy turned to regular translational kinetic energy. It gained, we have that 1/2 mv squared, it gained the velocity quickly, whereas in this case, it didn't gain as much velocity. It was moving slower. It didn't gain as much of that v in the 1/2 mv squared because some of this energy, it was allotted to our rotational kinetic energy. So I'm going to stop this here because I'm limited to 5 minutes, but we're going to come back and analyze this situation. Oops, I did not do it. Where am I going? Here we go. All right, let's come back.